Hey guys, I just wanted to do a quick video on order statistics. Um, Order statistics are kind of a cool example of random variables where you have dependence instead of the usual IID assumption. So, like usual, suppose we have some distribution. In this case, we're assuming that all the xi are random samples from a uniform on 0, 1. And we're trying to find the expected value of the kth order statistic. Okay, so what does that mean exactly? Well, the first order statistic is defined as the smallest value that that comes from the random sample right here. Second order statistic is the second smallest, and so on. Nth order statistic is the nth, or the biggest, or otherwise known as the nth smallest. And these are random variables, right? Because no matter what happens in your sample of data, um, the first element, or the smallest element in your random sample of your data is a random value, right? You don't know what that is until you've observed the sample. So these are all random variables, and therefore we can ask things like what's their expected value and what's their PDF. In particular, we need to get the PDF before we can calculate the expected value here of the kth order statistics. So we can do that just kind of by thinking through what has to happen for the one of these samples to become the kth order statistic. So meaning there are k minus 1 values less than this kth order statistic and n minus k values greater than. Okay, so let's see. So the PDF of x sub k, so that's the notation for the kth order statistic, is at a point x is given by, okay, well, we need to do some thinking here. So if the kth value takes on the value x, or this is PDF, so we're talking about density here, we're talking about in the neighborhood. But if the kth order statistic is in the neighborhood of x, that means that one of these random variables up here took on a value in the neighborhood of x. And that happens with probability density function f of x, x. So the rest of our data had to come from a kth order, had to come from less than x, right? Because the first order statistic, second order statistic, all up to the kth order statistic, all had to take on values less than x. So that means that we have, so first of all, what is the probability that a data point takes on a value less than x? Well, we know that's just the CDF f of x, and that has to happen k minus 1 times, and therefore the rest of them have to be larger than our point x, which happens n minus k times. Okay, now implicitly here we have a series of random variables in fx in the CDF to the k minus 1 that we've chosen, right? So we've chosen some set of these variables to be less than x, and then they occur with probability less than x. Essentially, what I'm getting at is that you can think of this as a binomial probability where a success is defined by being less than x. A failure is 1 minus being less than x, and you have n trials. But it's a little bit of a wonky binomial because you also have to multiply by the point density at point x. So if we just write this down, we have n choices. So if you think about this, we have n choices for the random variable density that becomes the value at x, right? So we have n choices for the random variable taking on the kth order statistic. Now, once we've mapped a random variable in this set to the kth order statistic, we have n minus 1 um, we have sorry, there we go. Okay, so we have n minus 1, since we just chose a random variable, and k minus 1 choices, just like in this, if you block out this part right here, just pretend that doesn't exist, then this looks just like a binomial density where probability of success is f of x, number of successes is k minus 1, and number of failures is n minus k, because n minus 1 minus k minus 1 is just n minus k. Okay, good. So we're getting close here. So we can now just take the expected value of this density. Let me subscript this properly. Okay. Oops, sorry. Okay, so that's the expected value by definition of the kth order statistic, which is just going to have this guy. So we solved for our density here. So we just take x times our density, right? And integrate that over the support. The support is just 0, 1 because we are dealing with uniform random variables. So now we can take out this part here that's not a function of x, pop it on the left, and then we can plug in our values for our explicit uniform density. So we know that the density of the uniform here is 1. We know that the CDF of the uniform is x, and 1 minus the CDF of the uniform is 1 minus x, n minus k. And let's see, we can combine these two into x to the k. Okay, cool. So we're getting close. So right now we're going to use a trick called the kernel trick, and this is a common trick in statistics where you look at this PDF right here, or this integral right here, and recognize it as the kernel, meaning the integral minus the constant of a named distribution. In this case, we'll recognize this. If you just look at the probability tables for continuous distributions, you'll see that this is clearly a beta PDF, which takes the form of this guy right here. Oops. X to the beta minus 1, or b minus 1, excuse me, where c is given by need a fraction here. C is given by the gamma function of a plus b over gamma b gamma a. Cool. Okay, so what can we do? Well, if we multiply this expression by C inverse, right? That's the same as multiplying by 1. Then we can pull C into this integrand and recognize this as a beta PDF given by right here. Just mapping. So we actually need to write this down because this is important. Where we map k, so alpha minus 1, or a minus 1 is equal to k. So a is equal to k plus 1, and b minus 1 is equal to n minus k. So b is equal to n minus k plus 1. Okay, we're getting very close here. So these are our values that we plug into this normalizing constant c, and this integrates to 1, right? Okay, so let's delete this. That just becomes 1. And let's write C inverse. So we know our expression for C is just this. To the negative 1. Cool. where gamma of a plus b, what's a plus b? Well, that's n minus k plus k, so that cancels plus 2, right? So it's n plus 2. Gamma of b is n minus k plus 1, and gamma of a is k plus 1, right? Okay, cool. So, sorry, I like to do this live, so it takes a little bit longer than if I wrote it out beforehand, but it's kind of more fun to see the steps written out. So we know that the gamma function for integers is the factorial function minus 1. And so this is actually n plus 1 factorial. This is n minus k factorial. And this is k factorial. And that's all inverted. Cool. So there's our expected value. We can do a little bit of algebra here to simplify. So n times n minus 1, choose k minus 1 is just what? That is just n factorial over n minus k factorial times k minus 1 factorial. And this is inverted, so let's just flip this. Oops, sorry. We're taking the inverse here, so I'm just going to flip this. Write this as n plus 1 factorial. Not factorial, factorial. There we go. Okay, what can we do? Let's get rid of these parentheses. What can we do here? Well, obviously n, this should not be L, this should be K. Sorry. These guys cancel, these cross cancel, right? So let's erase these. That gives us a k minus, k times k minus 1 factorial, right? So we can just erase that and erase the k minus 1 factorial. And that gives us n plus 1 times n factorial, which is just n factorial, except this is gone because we had n factorial over n factorial. Okay, and there we have it. That is the expected value of the kth order statistic. So now when you're doing your data analysis, you can just find the expected value of the kth smallest element. So the first smallest element is 1 over n plus 1 for the expected value. And the max is just n over n plus 1. So it's kind of an interesting result. And thanks for watching. Okay.